All right, thank you very much for the organizers to putting up this very nice conference and inviting me to present our work on these Gapless phases that arises from dipolar symmetry breaking. Sorry. No. All right, so I'm in the section of generalized symmetry and non-Fermi liquid. I think I fit in this section perfectly well because I'm going to talk about some generalized symmetry which relates to the spatial structure of the system, and also some interesting gapless phases and quantum critical point arises when this kind of exotic symmetry gets spontaneously broken. So dipolar symmetry is, we are considering lattice system. No, nothing works, okay. A lattice system with a conserved U1 charge, so there's a U1 charge conservation to start with. And in addition to that, we may consider certain dipole moment of the U1 charge conserved. So this dipole moment is a vector kind of symmetry. It depends on which direction you're looking at. In d-dimensional lattice, you would have d different dipole symmetry along different directions. So basically, it's the position of that lattice size times the charge density and then a projection to a certain direction. Right, so sometimes this is also called a center of mass position conservation. And the reason that people are interested in multipolar symmetry mostly arises from, or the earliest arises from the study of fermionic phases. People know that if the system preserves a dipole symmetry or multipolar symmetry, then single charge excitation cannot move, because moving the charges will change the dipole charge of the system. And if you gauge these multipolar symmetry, you also give rise to these symmetric tensor gauge theory, which are the effective theory describing some of the fermionic phases. And models with dipole symmetry has shown many interesting dynamical properties. Hilbert space shattering, meaning that even with a few conserved charge, you see your Hilbert space kind of fragments into sectors that cannot be connected by local movements, and there are slow thermalizations and anomalous hydrodynamics. So these are dynamical consequences of these dipole symmetries, which is not going to be the topic of my talk. We're going to be interested mostly in the ground state properties of a dipole conserving models. So just to mention that, dipole symmetry may be a little bit artificial, but there is possible ways to realize them in these tilted lattice cold atom experiments. The basic idea is if you add a linear potential along one direction, then different sectors with different dipole charges are separated in energy. So they're so separated in energy so that if you only consider low energy movement, you cannot hop between different, so you cannot change the dipole moment because of the energy conservation. So this is kind of an emergent conserved quantities when you are having these very large electric field. And these can be realized in one dimension, also in two dimensions. You just have to choose a direction of your field that's incommensurate with your lattice. And this has been realized in experiments, although they are most focusing on the dynamical properties of these dipolar symmetric models. Question? Yeah. There will be two dipole symmetry. Yes. That's the point of doing this incommensurate direction. All right. So that's some physical motivation that this dipole symmetry could be interesting. And what we're going to be, so there has been an early study by Ethan, Michael, and Santo. And there are many follow-up work I haven't cited here. But basically, they are considering these ground state properties of a dipolar symmetric boson models. The model is very kind of written in a way that's similar to the Bose-Hubbard model in two dimension, but with key differences. For example, the hopping term, if you think about it, it cannot be a single boson hopping. So in order to preserve the dipole moment, you have to hop 4 bosons. You have to involve 4 bosons. For example, 2 bosons from the middle hop to the 2 sides. So this procedure preserves the dipole symmetry. And another kind of hopping procedure you can think about is a dipole that's hopped from this line, from this row to the other row. Right? So any configuration, if you label it by blue and red, if you count the dipole charges 0, then that's a procedure that's allowed by the dipole symmetry. So although it's a hopping, but it's a correlated hopping involving at least four operators in the bosons. And then there, of course, some Hubbard interaction, on-site interaction would be preserving the dipole symmetry. So as a function of this correlated hopping, you may imagine these phase diagrams, and at small hoppings, we should expect a multi-insulator phase, which is incompressible insulating phase. And by tuning up this correlated hopping, what we can get first is a dipole condensed phase. A dipole condensed phase, meaning some of the dipole operators take expectation value. So the bosons get some bilinear kinetic energy. But if the kinetic energy is not enough to overcome the Mott gap, you're still in a boson gap phase, but there is a dipole symmetry breaking. There's a Goldstone mode associated with it. And then further increasing this correlated hopping, you are increase the kinetic energy of the boson, and then you may end up in a phase where the U1 charge symmetry is spontaneously broken in the end. And this is an interesting phase, which is called the Bose-Einstein insulator. And the reason for that is actually, so for the dipole condensed phase, you just have two Goldstone modes. This Goldstone mode is a vector field, so you have two components. And in the Bose-Einstein insulating phase, you can write down this phase associated with these bosons. And because of the dipole symmetry, the phase will be shifted under dipole symmetry to a constant times the x component or y component, depending on which component of the dipole you're looking at. Right, so such a symmetry constrains what's the low energy action for this phase. So the lowest order you can write down is a delta square times phi. You cannot write down the normal superfluid density, superfluid stiffness term because of this dipole symmetry. So that's a constraint coming from the dipole symmetry, and you would have a U1 charge conservation spontaneously broken as a compressible phase. But eventually it will going to be an insulator phase. So the way to see that is that we can couple this theory to the U1 gauge field, and because of this additional gradient, this coupling also comes with a gradient due to the dipole symmetry. Right. So this part is a normal coupling. So I should explain. So there are some gradient terms. This is an anisotropic term, which is not very important for our discussion. So the way to calculate a response theory is just to calculate the second order derivative with respect to this probe field. And because there's an additional kind of derivative in front of these gauge fields, you'll find that it's always going to be proportional. This is actually in any spatial dimension. So right, so that there's the whole discussion of where the symmetry can be broken or not. I think in two. So this particular I'm saying is two Goldstone mode is a 2-dimension. I can you can get quasi-Lorentz. Yes. Yes. Yeah, it's a quasi-Lorentz order. Right. So the point I want to try to make is that because of these additional derivatives, at zero momentums, the conductivity of the system is strictly zero. So that's kind of an interesting feature of this dipolar symmetric model. You can get compressible states, but there are also insulator in the zero momentum, in the DC limit. Okay. So what we are trying to do is to try to explore some universal properties of models with fermions, with dipolar symmetry, focusing on the properties of phases where the dipolar symmetry is spontaneously broken, to see what kind of effect of this dynamical constraint can lead to in the low energy. So we're considering two different situations. If you have fermions at generic fillings, what we see is that this Goldstone coupling between the fermions and between the fermion and Goldstone actually leads the system to be a non-Fermi liquid state at zero temperature. And if you have fermions at generic fillings, then you would have band structure of the fermion, and filling the band with non-trivial topology actually can change the dynamics of the goldstone. And the topological phase transition in the presence of these spontaneously dipolar symmetry breaking also is a kind of interesting transition. Yeah, so there are some ongoing efforts. So there are a lot of experts in this audience who are really expert on these critical phenomena. So I want to also seek some comments on this, the last problem. So these are the papers that would be relevant for this talk. So dipolar symmetric Fermion model is very simple. You can write down any Fermion model, any Fermion hopping operator that will carry a non-trivial dipole moment, and you just write down dipole conserving Hamiltonian is just the hopping of dipoles, right? So you can do vertical hoppings, you can do hoppings along the same directions. They will be characterized by this general hopping matrix. And there, we can also allow some chemical potential terms, Hubbard terms that are on site, which doesn't break the dipole symmetry. So really, it is very hard to solve these interacting models, and that's not what we're trying to do. We're trying if I was doing that, then I'll be running to some numerical method. What we are basically trying to do is to explore if with mean field theory what kind of states we can get. And of course, if you do a naive mean field theory, then the fermion will get some kinetic term and then get some dispersion relation. Right? So just to show that there's variety of states you can get by this simple mean field, which I know is not really reliable, but we're trying to focus on phases that can emerge under these conditions. For example, you can get Fermi surfaces with spin polarized. And you can also get Fermi surfaces that's spin degenerate. You can also get some one-dimensional Fermi surfaces just by tuning the fillings and also by tuning some of the parameters in the hopping matrix we can get. So these are symmetry breaking phases. If their symmetry is not broken, I really don't know what is the fate of that phase. Maybe it's an insulator, I don't know. And this symmetry breaking phase we have a good handle because it has a mean field Fermi surface that we can work with. Right? So at low energy mean field level, we have a Fermi surface, and beyond mean field, we should think about how the goldstone is coupled to the Fermi surface. Right? So if we do this mean field decomposition, this one is the dipole operator that gets the expectation value and the phase, and this phase is the goldstone, say, along x direction, and this coupling essentially is like a gauge field coupling. Right? So anytime you hop a fermion from this side to the other side, you multiply by the phase that's given by this dipolar goldstone. So the D component vector goldstone mode coupled to the fermion as just like a spatial part of a gauge field So this goldstone fermion coupling is non-vanishing. The zero momentum limit is actually there's a general theorem by Watanabe and Vishwanas, 2014, that says if you have generators of the goldstone that's not commuting with the translation operator, then you would have such a non-vanishing zero momentum goldstone coupling. So indeed, for a dipole symmetry, you can check the dipole symmetry and translation symmetry. Their commutator give you the total charge of the system. All right, so that smells like we're going to get some non-Fermi liquid because we are in the end we get some Fermi surface coupled to a goldstone, and that goldstone couples like a spatial part of a gauge field, right? So there is one little subtlety which is not so important. So the effective theory is very standard. You have some Fermi surface coupled to this goldstone mode. And we know that this goldstone modes, they're not really gauge fields. They don't have gauge invariance, so there are two components. The transverse and longitudinal component of the gauge field are both physical. If you do the calculation, we know that momentum transfer parallel to the Fermi surface couples most strongly to the boson mode. It dampens the boson mode. So that means that only the transverse component of these goldstone gets a Landau damping, and the longitudinal component of this goldstone doesn't get a Landau damping. So the longitudinal components gets dynamically decoupled, and the transverse degree freedoms in the end behave like a gauge field. So in the end, this problem indeed maps to a spin non-Fermi surface coupled to a dynamical gauge field. So you'll get some.
If you take this T and calculate fermionic self-energy, you get divergences immediately.
Yes, yes. You should get everything that's expected for the non-Fermionic theory. Right. So the non-Fermionic physics happens when the other state sets in, and if you calculate the scale of the non-Fermi liquid, so you can calculate the coefficient of this omega 2/3 state. That coefficient has an energy scale. So that energy scale is roughly on the same order of this ordering transition temperature. So you can also imagine a situation where the system doesn't have microscopic, it doesn't have a dipolar symmetry, and that could be some normal hoppings of the fermions. Those will be perturbations in the low energy, acting like a mass term for the Goldstone bosons.
So here, the Goldstone mode has a very anisotropic.
Yes.
So I imagine different parts of the Fermi surface may have different behavior of self-energy.
Not really. I guess you would have Goldstone along different directions, and the. So the coupling is just the velocity coupling, basically. I should assume that I'm assuming the rotational symmetry. Maybe that's something you are concerning about. If you have lattice, there indeed is going to be anisotropic terms, which couples the transverse and longitudinal modes. And because of this dynamical decoupling in the end, so only the transverse mode will be surviving in the end.
But the largest self-energy come from direction of the longitudinal mode?
So sorry, you mean the longitudinal one? The longitudinal one simply at one loop doesn't get damped.
Right, but this means that it gives larger contribution to self-energy.
No, so this damped mode gives larger contribution, and the one that's not damped gives smaller contribution. That's fine.
Go ahead. Not clear, but I don't.
Okay. Right. So I was saying that if you have a perturbation that's in the UV, it's going to be breaking the dipolar symmetry. Then there is a parameter you can tune, and this parameter has scaling dimensions 3 halves in this non-Fermi liquid fixed point, and you can define a temperature regime or frequency regime scale with this parameter as r to the 3 halves. So basically, as you lower the temperature, if you don't have any breaking of the dipolar symmetry, you find the regime of non-Fermi liquid, and then if you have some symmetry breaking, you find there's a crossover between the non-Fermi liquid physics to the Fermi liquid physics at low temperature. Okay, and this may be related to what Senko was talking about, but maybe it's not exactly. So we could also suppose there's only one direction. We have dipolar symmetry, and that direction dipolar symmetry is breaking. So the dispersion relation partly come from the bare hopping along one direction and dipole condensation along the other. And indeed, in that case, you would have some anisotropic coupling between the Goldstone and the fermion, and you would get hot spots. Say this is along the x direction, you have a dipole symmetry, then there's hot spots here, and there's cold spots here. So you could get part of the Fermi surface non-Fermi liquid and part of it kind of Fermi liquid-like. So it's kind of an interesting model in this sense. So that's about fermions with generic filling. So it's mostly mapped to the spin-on Fermi surface problem, which we know we kind of know the low, and we kind of expect what happens at low energy. But so the next topic is to talk about if you have integer filling. So we could also come up with some mean field theory. You have some dipolar symmetric models. This model is designed to be such that if you have a naive mean field, it will have some non-trivial band structure. So this mean field theory is not meant to be precise, but just to show that there are possible phases that could be emerging at low energy. So if you do some kind of, so this dipole hopping is designed such that it mimics spin-orbit coupling. And if you do some mean field calculation, indeed you get some symmetry unbroken phase and there's symmetry breaking phase where the band could have non-trivial topological numbers, right? And there's some quasi-1D physics as well. So the mean field band structure can have non-trivial topology. The question is what this topology is doing to the Goldstone mode. And if you have a topological phase transition between the C equal to 0 and C equals to 1, is it going to be similar to the quantum Hall transition? Is it going to be very different from the quantum Hall transition? A very simple thing you can do is that in the phase where the fermions are gapped, you can integrate out the fermions, and then that generates some effective theory for the Goldstone mode. There's some kinetic energies. And there are also a topological term that's speed out because of the gauge field couples to the fermions just like a gauge field. The Goldstone couples to the fermions just like gauge field. So if your system have non-trivial chain number, then you get some linear derivative in T terms, and C equals to non-zero. So if C is equal to 0, then you just have two Goldstone modes coming from two different directions with linear dispersion. And if C is non-zero, and then if you solve this theory, you find that you get two modes. One mode is gapped, the other mode is gapless still, but the dispersion becomes quadratic. So the exact same procedure you can find analogy in gauge theory with the max term coupled to the gauge field. But in that case, there is indeed a mode that's quadratically dispersing at 0 energy, but that's a pure gauge mode, so it's not physical. So we know that Chern-Simons coupled to added to Maxwell is going to be a gap theory. But in this case, it's really different because both of the components of the Goldstone mode are physical. So you'd get a physical quadratic Goldstone mode in the end. So this quadratic, this Chern-Simons term has also emerged in some other contexts in these quantum vortex of rotating boson gas. There's this Kachinka mode that was discussed in this set of papers. So they also find these interesting response theory for the phonon modes in those systems.
Do you mean quadratic dispersion or not?
Yeah, so I mean the quadratic dispersion.
No, you mean for the Goldstone mode, the first term?
So this terms is not quadratic. So these are kind of Z equals to 1 dispersion. Only when you have this topological term from the fermion band structure, you will get Z equals to 2 dispersion. All right, so by tuning some parameters, mean field level, you can drive a transition between the topological phase C equals 1 and C equals 0. And we expect, because the Goldstone mode acts like a pseudo gauge field, maybe this transition is similar to the quantum Hall transition, which was studied years ago. Many of the audience has studied this property problem. So the low energy theory for our transition is what we can imagine there's going to be a Dirac fermion that changed its sign due to the topological change, and then there's some regulating half-level Chern-Simons, and then there's this Goldstone action which has Z equals to 1. So there's some key differences in this low energy theory. One is the Goldstone mode does not have gauge invariance, meaning that both longitudinal and transverse are going to be physical, and phi only has the x and y components in 2 dimensions, and that breaks the Lorentz invariance of the system. So we could do some naive RPA calculation for this transition, and so this is going to be standard Dirac fermion bubbles, and there's some odd part coming from the Chern-Simons term, and we can try to decompose this fermion's self energy for the bosons into the longitudinal mode and the transverse mode of the bosons. And the peculiar features that we find is that, so this piece you would expect. For the transverse mode, you will get a p-linear, omega-linear term coming from the Dirac fermion. And for the transverse mode, you actually get a correction that's omega squared over square root of omega plus p squared. So this is something, so this term will be more relevant than the bare dispersion question.
So trivial Dirac fermion does not have Dirac
Yeah, so zero density, no Fermi surface, yes. So that's where it's gonna be, it's kind of surprisingly get these kind of singular corrections. Although it's singular here already, but yeah. So that's where so omega square over square root of omega plus c square, that's more relevant than the omega square. So in the low energy IR, you would keep this term and keep this p square term, and then you get the dynamic. So the dynamic exponent for the longitudinal mode get a stronger correction, which has z equal to 3 halves. And the transverse mode still have z equals to 1. So dynamically, these two, the coupling will be, the theory will be decoupled with the transverse mode in this case, but strongly coupled to the longitudinal mode in the low energy. Okay. This is just a digestion for how we think about. It's not very terribly important. You know, so this is the coupling. This is coupling phi with the current J, and you can project to the longitudinal mode and use the current conservation. You find that the longitudinal mode coupled to the fermions as J0 with this omega over p factor. Thank you. And you can use the JJ correlator and find that the self-energy coming from the going into the longitudinal component scale as omega square over p in the low energy. And if you use that damped boson propagators to calculate some fermion self-energy, you find that there's even singular terms coming from this damped boson, and that's going to be dominating in the low energy. So typically, this kind of singular Fermi energy, self-energy comes from a non-zero density of Fermi surface, but it's kind of surprising we find this also in the theory that's Dirac fermion coupled to some bosons. So the question is, can we justify these RPA results with some controlled scheme? And there is a famous problem. So we would naively do some large n, so n flavor fermions coupled to these bosons, and this usually works for fermions coupled to gauge field problem. The issue is that if you calculate the fermion self-energy, it's going to be proportional to 1 over n, because you drag two of these vertex, and the singular self-energy in the IR gets a boost. So G inverse is proportional to 1 over n, so G itself is proportional to n. So we get this kind of famous problem in Largen theory of Fermi surface coupled to gauge field. So every time you use the fermion propagator, you get an n boost. And that is bad because the Largen theory will not be controlled in the IR. So it's a similar problem in this Fermi surface, Largen Fermi surface. Right. So we kind of realized this problem only recently. But there is a potential cure for that that was developed by Central and company. So what they do is to do a non-analytic generalization for the boson propagator or boson kinetic energy. So they can change the p square kinetic energy to. So in our situation, we can do a similar generalization. We do change the p square to 1p to the 1 plus epsilon, and this epsilon is our control parameter. So z will, the dynamical exponent in this case, will become epsilon over 2. So if you use this epsilon over 2, 1 plus z epsilon over 2 bosons to calculate the fermion self-energy, you get a kind of enhancement of 1 over epsilon in this fermion bubble. So in the one loop fermion self-energy. So if we keep this number to the order 1, there's a hope that we can control the theory with Largen and both epsilon and Largen. So this is, we only recently realized this is maybe a way to solve this. So it's a work in progress. We can start with this UV Lagrangian and then try to calculate some perturbative RG, and we still need to check. These cross diagrams are smaller than these rainbow diagrams, and this kind of bubble diagram with an eddy in the middle is smaller than these wave function renormalization. So these are requirement for the vertex correction to be subdominant in this control scheme. Yes.
If you calculate within the same scheme K-dependent cell damage, sigma of K.
Yes.
Of course, the sigma of K will be much smaller than the sigma of D, but do you get log there?
You mean log of Q?
K log K.
I think we do not got some log.
Another problem for this.
Right. Yeah, so that's why I'm listening to any comments we can get from this problem. Yes. So there's a hope that we can control this theory with this double expansion. Right. So anyway, so if the double expansion works, then it just means that the RPA will be leading will be a leading order effect. So what we get is just a z equals to 1 theory transition to a z equal to 2 theory. This z equal to 1, you have 2 Goldstone mode and 1 band insulator z equal to 2. We have 1 quadratic Goldstone with a topological band with edge modes. And in the middle, we get some z equal to 3/2 theory. Both the fermion and the boson get some strong renormalization. Yeah, so that's the topological phase transition. Yeah, I get to the summary. So summary is that the dipolar Goldstone acts like some U1 gauge field coupled to fermions in the low energy, but with some key differences. At generic field, we get non-Fermi liquid. That's almost the same as the old story of spin non-Fermi surface. But at integer fielding, this topological phase transition has some interesting additional features that we didn't realize before. Yeah, so there are many questions. What's our other scheme that can control this? So maybe some matrix margin could do this calculation, and if there's any numerical efforts. I should mention there are many numerical efforts in one dimension already to do this dipolar symmetric models, finding these Bose-Einstein insulating, possible Bose-Einstein insulating phase. So I didn't cite them, but there are many studies in one dimension. Maybe there's some, could be motivating some study in 2 dimension as well. So there is a gapless edge mode on the boundary of this system, which is coupled to the Goldstone in the bulk. So it's interesting to ask what's the fate of this edge mode when the coupling is taken into account. And I have only tell you a very cold atom realization for dipolar symmetry. So a very pressing question is how to realize this, maybe in a quasi-solid state setup. So that's some questions I like to think about in the future. Thank you.
Thank you very much. Thanks. So before going to questions, let me thank all 4 speakers for being on time. That make my work very easy.
I have 2 questions. So one is, when you integrate fermions, you usually get a Chern-Simons term.
Right.
But here you're focusing only on the time-dependent part of it.
Right. That's
so where's the spatial part?
The problem is we only have spatial part of the Goldstone. So we only have phi x and phi y. We don't have phi 0. So we only take one component of it. If you do include the probe gauge field, then it's going to be another few terms.
Like a mutual term.
Yeah, there will be a mutual term. That means that the vortex of the Goldstone would carry some charge.
And the other question is, so you're looking at dipole condensate and how it couple,
right.
What terms you induce from the fermions. Have you looked at the charge condensate phase where you have this Lifshitz model?
Oh, so that we need to go into some superconducting instabilities.
Yeah, they both condensate.
Which I haven't really looked into. Maybe this positive critical point is unstable to the superconductivity. I have no idea whether that will happen or not.
Thanks.
I have a question about just the first step, the mean field. Other competing phases that don't have fermion hopping, something like, I don't know, dipolar solids or density waves, where you don't decouple in terms of fermion hopping, but into something else. And the question is whether they're competitive or whether the fermionic phase, the hopping phase.
Yeah, so I have to admit that when we do this mean field, it's kind of a restricted mean field. So we didn't really look for like density waves or symmetry breaking, translational symmetry breaking states. So Yeah, so that's not the purpose of this mean field, because we're just demonstrating that there could be such topological bands. That is, yeah, we're more focused on this universal properties after you get into the dipole symmetry breaking phase.
Okay, thank you.
Yeah, so that will be answered if you do have a lattice model and then solve it more honestly with.
Or at least mean field, but allow for other types
yeah,
of
yeah.
the parameters.
We can do that as well. Yes. Yes.
Yeah, go ahead.
So earlier in the talk, you mentioned that the longitudinal field decouples, longitudinal Goldstone decouples because it acts like a pure gauge from the perspective of the fermions?
No, so in the Fermi surface problem, the longitudinal mode decouples because its momentum is just not parallel to the Fermi surface, so it doesn't couple to the Fermi surface most strongly. Right? The boson that couples most strongly will connect parts of the Fermi surface with almost the same energy. This momentum is going to be changing the energy a lot. So that's going to be irrelevant. And the relevant coupling is this transverse mode, where the momentum is parallel to the Fermi surface.
From the lattice perspective, can I think of it as a longitudinal modulation? The fermion does not see that because it cannot pick up an Aronow-Bohm phase from such a...
I think it's simpler than that. What I understand is mostly from this energetic reason that you want to connect Fermi surface with similar energies to get strongly damping.
Yeah, I have a very simple question about the experimental realization. So you said in the beginning that this is reasonable if you have a tilted optical lattice, which seems to break the 2D translation symmetry on the lattice. But the effective theories you write down in the end have 2D translation symmetry, right? So how is that restored in some dynamical way?
You're asking specifically for the 2D system?
Yeah, exactly. I guess I could ask about any dimension, but the potential will break the translation symmetry, right?
Yeah, I don't have an immediate answer for that. I think in this paper they might mention something about that. Yeah.
Maybe it's a timescale issue. Like maybe for some sufficiently long but finite timescale, you still have translation symmetry, but it's broken. Okay, I don't know.
I don't know on top of my head. Sorry.
One question.
So for the dipole symmetry, that symmetry breaking that triggers the non-Fermi liquid, I wonder, does the Goldstone boson of the dipole symmetry breaking, would it enhance or suppress the pairing channel for that?
So in this problem is mostly mapped to the spin-on Fermi surface case. Oh, I forgot to mention my student, which is really the hero of all this work. Because it's mapped to the spin-on Fermi surface, we know from work of Max it's going to be stable to superconducting.
So because you have a quadrupole spontaneous symmetry breaking, which would probably also trigger non-Fermi liquid, would just enhance pairing.
So quadrupole, I would imagine there's some symmetric gauge field that couples to fermions, which I still don't know how to study. So quadrupole, maybe the gauge field for quadrupole could be kind of.
About the last part of your talk, where you had this churn number changing transition. So Sangsik will correct me, but I remember that in his paper, this violation of 1/n counting and so forth, somehow it had to do with the fact that you have the Fermi surface, right? So you can have kind of these flat directions along the Fermi surface and have some kind of double line notation to count which diagrams will violate 1/n counting and which ones would not. Now, when you have just a singularity at the Dirac point, I'm a bit surprised that same issues come up. Or
I'm just coming from a naive counting perspective. Where we look at higher loops, every fermion propagator you write down will have an enhancement factor of n, and there's no 1/n to counter that. So basically, if you do large n counting with this self energy of fermions, all these diagrams will be more important than the one loop diagram.
What about the momentum dependence of the Fermion propagator?
Same question.
So the momentum dependence also gets some singular correction, which is also proportional to 1 over n.
Oh, I see.
So I think there's overall 1 over n in the.
I see. It's both the frequency and momentum dependent.
No, but they're with different powers.
Yeah, so that
Frequency dependence omega 1/2, and I guess moment dependence will be no more than log, but there will be singularity.
right.
I see.
Actually, I kind of wanted to answer a previous question. Like when you have this electrons moving in this slanted well, like there is an effective Hamiltonian you can write down that is translation invariant. I think it's basically just because the electrons don't, because you have dipole conservation symmetry anyway. Like, you know, there's no like net motion of electrons because of an electric field because they're stuck in the wells anyway. So there is an effective translation invariant Hamiltonian.
I see. Okay, good. Thank you.
More questions? If not, thanks very much.
Thank you.